Okay, this is going to be an introduction to the direct comparison test, and it's kind of based on this. Up until now, and the things that you've been looking at, whenever you try to figure out whether a series was convergent or divergent, it fell into some categories. So, for example, you had the geometric series, which was pretty easy to determine. You had the p-series, which is another series that's very easy to determine whether it's convergent or divergent. But the farther you get into this, these things will become a little bit more complicated. So the idea, if you look at this particular problem right here, it's not a geometric problem. It's not a p-series problem. So the question is there some series that's similar to this that you can relate it to? So the process as you go through this will be like this. You'll start with an original series, and the idea is to find a second series that's comparable to it, that has similar characteristics to that series, except usually the second series will be simpler. So find a simpler series, and if you can show that that simpler series either converges or diverges, it will tell you something about the behavior of the original series. So it's called the comparison test because you're going to start with an original series and compare it to some new series. Now let's take a look at the rule and see what the rule looks like. So the rule actually looks something like this. If you look at it in a book, usually it reads like this. The direct comparison test says if you have a series A sub n that's less than a series B sub n, and then it runs through these steps. If B sub n converges, then A sub n also converges, or if A sub n diverges, then B sub n also diverges. Now, this definition, I don't use it very often because to me it's a little bit confusing. Because if you set it up like this, sometimes the original series is A sub n, and your comparison series, your test series, is B sub n, or sometimes the original series is B sub n and the test series is A sub n. And it makes it confusing which one's which. So I tend to work with another definition, and I'll put it up here where you can see it, is to me, it's the same thing, but it just makes more sense to write it out like this. Now the idea is you're going to start with an original series, you're going to come up with a test series that's simpler, that will tell you something about it. So it's all based on what's going on with the test series. And if you read it like this, this makes this blue part up here, I think, a little bit easier. So the idea is if the test series converges and the original series is less than the test series at every point, then the original series also converges. Now the other possibility, if the test series diverges and the original series is greater than the test series at every point, then the original series diverges. So again, to give you a little bit better look at it, let's take one quick look graphically at what this thing actually looks like. So if I looked at a graph, it'll look like this. Now it's all based on this. I've got an original series, and I'm going to come up with some kind of a test series to compare it with. Now let's suppose that I came up with the two possibilities. Either the test series is going to converge or it's going to diverge. Can't do anything else. So first of all, let's look at the possibility that it converges. Now, if it converges, the series of dots that make up the test series, the sequence would have to look something like this. So for a series to converge, the sequence that makes it up has to be decreasing and approaching the x-axis, and has to be approaching 0. So if it looks like this, and we're going to put a little arrow here, this would be a case where our test series, in this case, you know that the test series converges. So we'll put converges right here. So now the question is, what's going on with the original series? So this thing says this. If you know the test series converges, it has to have this shape. Now, if the original series is less than the test series at every point, we'll put the original series kind of in blue. All that means is every blue dot that I put on here is going to be below the red dots. So this means that the original series, each point on the original series is less than a point on the test series. So again, these blue dots here are the original series. So that's going to be the original. Now, I want to emphasize here is that if the test series converges, and this thing is, and we'll underline this, less than the original series, the blue dots have to be below the red dot. And it's kind of like the squeeze theorem in a way. If the red dots are converging and the blue dots are less than the red dot at every point, then the original series must also converge. And that's what all this thing says. So again, if the test series is converging and the original series is less than the test series, then the original series must also converge. And that's what this definition says. Now, the second possibility is this. Suppose that you come up with a test series, and the test series diverges. And what that means is that it's not approaching the x-axis fast enough. It could look something like this, and this would be a case where, and I think I'll go back and put this in red again. This will be a case where the test series diverges. So now, if the test series is diverging, what's going on with the original series? And we'll go back to our blue dots again. Now, in this case, if the test series diverges and the original series is greater than the test series, then that means that each of these blue dots would be above each one of the red dots. So it might go something like this. So again, these are the original series. So if the test series diverges, any series that's greater than the test series must also diverge. So the original series will also diverge. Now, before we go on, there's actually two other possibilities. Suppose that you knew this. Suppose that you knew that the test series converged, but the original series was greater than the test series. So suppose it turns out you'll know that this one converges, but suppose when you do your test series, you find out that the test series is above the original series. So maybe it looks something like this. Then in this case, since the test series, since the red series converges and the blue series here is above the test series, you don't know if it converges or not. You'll never be able to tell. So in this case, the test fails. So again, this thing only works if the test series converges. You can only show that the original series converges. You can't tell anything about what happens if it's greater than. Then you got the same situation over here. If the test series diverges, but suppose that the original series turned out to be less than this one, then again, this rule only works if it's greater than. So if the original series turns out to be less than the series that diverges, again, you can tell nothing. You don't know whether this series is going to converge or diverge. So again, the test fails. So really, you've got four possibilities when you use this thing. Either it converges, it diverges, the test fails, or the test fails. So we'll look at all these possibilities as we go through. So finally, let's get around to doing some problems. Okay, the first problem looks like this. Get rid of these little marks. And it works like this. So the idea is, here is a series, and I want to try to figure out whether it converges or diverges. But the deal is, it's not geometric, it's not a p-series, but it's kind of like a p-series if you look at it. So the first thing I'll do here is I think I'm going to go ahead and, if you can simplify it a little bit, simplify it. So I'll take this 2 and bring it outside the summation sign. So this will be 2 times the summation of 1 over n minus 1 as n goes from 2 up to infinity. Okay, now I want to try to find a second sequence that's similar to this, that behaves in the same way. And one way of doing this is to use what's called the dominant term rules when you're working with limits. Now, if you're not familiar with these, you may want to back way up and watch the original limit videos again. What happens when n goes off to infinity? And again, the logic goes something like this. I've got 1 over n minus 1. As n goes to infinity, this term is going to get larger and larger and larger to the point that the minus 1 is going to become insignificant or basically disappear. So if you go way off to the right, 1 over n minus 1 actually will become the summation of, it will behave as if it's the summation of 1. And so what this is going to be, this was my original series. And this is going to be my new, what I'm going to call a test series to check it, compare it against. So now the idea is, if I can find out what the behavior of this one is, I can get the behavior of this one. So on this one, now first of all, you have to recognize, hopefully it's a series you recognize. A lot of times this will turn into either a geometric series or a p-series. Well, you can think of this as being 1 over n to the first power, the summation of 1 over n to the first power. Now, a reminder, what a p-series is, if you had the p-series test, and you should be familiar with these, that's 1 over n to the p power. And again, if P is less than or equal to 1, it diverges. If P is greater than 1, remember it converges. So that's P-series test. So since this is the 1, you can actually go ahead and make this conclusion. We'll go ahead and put it right here. This is a P-series with P equal to 1, therefore it diverges. That's what this is here. If P is greater than 1, then it would converge. Well, in this case, we've got P is equal to 1, so this test series diverges. So you know that the test series diverges. Now, where that puts you in the problem, let's go back up here and take a look at the graph. At this point, you're now down to this case 2. You know that the test series diverges, so it could look something like these little red dots right here. So at this point, since the test series diverges, the best you can hope to do is to show that the original series diverges. You can't tell anything about whether it converges or not. The best you can do is converge. And also, it will only diverge if the original series is greater than the test series. So you know that the test series converges. The next question now is the original series greater than the test series? So let's take a look at that. Now, you're hoping that your blue dots will wind up above. So you've got the red dots. If you can show that your original series is greater than this, then you can show that both of them diverge. So back to this again. Now the next step would be to this. Here's what I want to know. I need to know, is the original series, and again, I'm hoping that it's greater than the test series. So I want to know, is the original series greater than the test series? And I'll put a question mark above that because at this point I'm not sure. So the idea is to write down the original series, and the 2 won't make any difference because if it's going to converge, then it'll be based on this. Multiplying, if it's convergent, multiplying by 2 doesn't make any difference. So I'll compare 1 minus n minus 1, and I want to know, is that greater than the test series? So you're comparing the original series to the test series. But again, we'll put a little question mark above this because at this point I'm not sure. So if I can show that the original is greater than the test, then again, by the rules, if the original is greater than the test, you've proved that the original series diverges. But how do you do that? Now, you can use different arguments. You can make the argument of this. No matter what number you pick for n, if you, in the denominator here, if you pick the same number here and subtract 1, this denominator will always be smaller than this denominator will be. And with a fraction, whichever one has the smaller denominator makes the largest fraction. Or you can pick a few specific points. I think I might do that real quick. Let's suppose we pick n is equal to, let's just suppose I pick 10. Then on this side, I would have 1/10, and I'm curious, is that greater than, on this side, I'd have 10 minus 1, I'd have 1/9. Well, indeed, 1/9 is greater than 1/10. If you went out to 100, you would have 1 over 100 divided by 1 over 99. That one's bigger. So no matter what you pick for n, if you take away 1, this fraction will always be greater than this fraction. So what that does, that tells you that this is true. And that says that the original series, term by term as you go way off to the right, is greater than the test series. So back to our definition again. And let's like one more thing. The first thing you had, you know that the test series diverges, and you've just showed that the original series is greater than the test series. So again, if you show that the test series diverges and the original series is greater than the test series, then your conclusion is the original series must also diverge. So now you can finally conclude that the original series diverges. So the original series is going to diverge. Okay, so again, the idea is come up with a series to compare it to, figure out what's going on with that test series, then compare the original series to the test series, and you'll know what's going on with the original series. Now, in the next problem, the only difference is going to be this. In this case, the test series diverged and the original series diverged. Suppose we had this, though. Rather than 2 divided by n minus 1, let's change the problem, and the only difference is going to be n plus 1, and see what a difference that makes. So If I change it, now it looks like this. So again, the only difference in these problems is this is now plus. But I'll follow the same series of steps. So initially, I'm going to write this as, again, I'll bring the 2 out in front just like I did last time. This goes from n equals 1 to infinity, which gives me 1 over n minus 1. Now, again, I need to come up with a test series. And again, use this logic. Ask yourself, what happens to this as n goes way off to the right? Well, as n goes way off to the right, n becomes the dominant term. The minus 1 is like it doesn't even exist, and this thing will actually turn into the summation of 1 to n. And again, just like we did last time, that's the same thing as the summation of 1 over n to the first power. And you can show that this, and again, I'll kind of write it like this. Here is your original series, and this is your new test series. Well, you can show that this thing diverges, this test series diverges by the p-test, just like we did last time, so that you know that the test series diverges. Now again, where that puts you in the problem, back to this again, you've got this situation right here, case 2. The test series diverges, and so the best you can hope for is that your original series will be greater than the test series, and you can conclude that it diverges. So back to the problem. Again, what I want to know is I've got the original series, and because the test series diverged, I'm hoping that the original series will be greater than the test series. If it is, then I know that the original series diverges. But is it? So again, let's go ahead and put our things back in here. I'm sorry, one correction, it should be a plus 1. So this would be 1 over n plus 1. And this is, I want to know, is this thing greater than 1 over n? And again, I've got a question mark. Now, let's take a quick look at what we had last time. Go back to here. Last time, it was n minus 1, and it turned out to be true. But in this problem, what we'll have is this. Again, I'll kind of use the same thing. Suppose I put in a 10. So if I let n be equal to 10, and this side I would have 1/10, and I want to know is 10 plus 1, this would be 1/11. So is 1/11 greater than 1/10? And the answer is no. The bigger the denominator, the smaller the fraction. So this would be false. And again, you can use bigger numbers if you wanted to. But what you can show then is, since the denominator on this side is smaller than the denominator on this side, that this fraction will always be smaller than this fraction. So this thing right here is not true. So the original is not bigger than the test function. So what this tells you is that the original series is less than the test series. So the test series diverge, but the original series is less than the test series. So now back to your finger. So you had a case where the test series diverged, but your original series is not greater than the test series, it's less than the test series, so it's a situation that looks like this, and the best you can do is to conclude that the test fails. So we'll go back to here again. So the final thing would be this: the test fails, and you'll either have to pick a new series to compare it to or try another test. So in this case, the test fails. So again, in the first example, the comparison test, the test of the series that you're comparing it to diverged, and the original was greater than the test, and so it diverged. But in this one, the test series diverges. Your original series is actually less than the test series, and therefore the test fails. Okay, let's try another example. And this next example looks like this. So suppose you have, again, 1 over 2 to the n squared. Now, what are you going to compare it to? Again, think about this dominant term thing. If you go way off to the right, then the dominant term is going to be n squared. Eventually, the plus 3 will become insignificant, and really 2 is going to become insignificant. It really comes down to just the dominant term, which is 1 over n squared. So what that's going to look like, it would be 1 over, it'd give you a little bit of a hint, this thing should be 1 over n squared summation. So what this will be, this is going to be the test series, and this is going to be your original series. And you want to compare. So now, the next question to ask yourself is, what's going on with the test series? Is it converging or diverging? And this is another case of a p-series. You can think of this as being a p-series test. And by the p-series, again, if the exponent is greater than 1, then that tells you that this test series, so the test series converges. So it's going to converge. So again, if p is greater than 1, then a p-series converges. If p is less than or equal to 1, then it diverges. So you know that this test series converges. So again, graphically, let's take a quick look and see where that puts you. That puts you now up at this one. The test series converge, so you've got this red series of dots right here. Now, in that case, the best you can hope for is that the original series is less than this, and it will also converge. So you're hoping that your original series will turn out to be less than the test series. Let's see what happens. Okay, so again, what I want to know, in this case here, I want the original, and I want to compare that to the test, and I'm actually kind of hoping that the original series, and I'm going to put a question mark because I'm not sure, but I'm hoping that the original series is less than the test series. Because if it is less than the test series, then that means that it's in this situation right here, and if the original series is less than the test series, I can conclude that the original series converges. Otherwise, the test would fail. So again, put the original series here. This is going to be 1 divided by 2n squared plus 3. And I'm hoping, and I'll put a little question mark here again, I'm hoping that that's less than the test series, which is 1 over n squared. Now again, you can use the same logic. Whatever the denominator is here, whatever number you put in here, if you square it, it's going to be a certain number. But then if you take that number, square it, multiply it by 2, and add 3 to it, this denominator on the left will always be bigger than the denominator on the right. Therefore, the fraction on the left will be bigger than the fraction on the right, which implies that this is true. So the fraction on the left is always going to be bigger than the fraction on the right. It is true. And what that means is that the original series is less than the test series at every point. So you had an original series and a test series. Now again, back to your rules. What the rules look like would be this. You know that the test series converges. Your original series, you've just showed that the original series is less than the test series at every point. Therefore, you can draw this final conclusion. The original series must be converging. So let's go back. And the final thing would be that the original series converges. So again, if the test series converges and the original series is less than the test series at every point, then you can conclude that the test series converges. So let's try a couple more. Okay, so this one is a little bit harder to try to find out what the test is to converge to, but again, we'll use our rule on dominant term. So what I'm going to do is think of it like this. If I go way off to the right on this thing, and first of all, I think I'll do it like this. The very first thing to do is I've got a constant 4. I'll just go ahead and pull that 4 out. So this will be 4 times the summation of n equals 1 to infinity of 1 over, and this is going to be the square root of n cubed plus 2. So now what happens is you go way off to the right. Well, if you go way off to the right, n cubed is going to get larger and larger and larger, and this thing is going to become basically insignificant. So it will turn into this. So it would be like having the square root of n cubed. So as you go way off to the right, basically the plus 2 disappears. And you can rewrite this as 1 over, now remember the square root of n cubed would be n to the 3/2 power. But what this gives you again is basically a p-series. So you've got n over this thing to the 3/2 power as n goes from 1 to infinity. And again, if this is my original series, then I've come up with a new series to compare it to, and this is going to be the test series. So now the next step is to try and figure out what's going on with the test series. Is it converging or diverging? And again, this is a p-series test with p is equal to 3/2. And again, if p is less than or equal to 1, it diverges. If p is greater than or equal to 1, it converges. Well, this is greater than 1. So this tells you that this test series converges. So you changed your original series into a new series that you know something about. The test series converges. So again, let's go back, and now you don't figure out what's going on with the original series. Again, looking back at this, you're in this case right here. The first step you did was to show that the test series converges, so you're in this situation. Now, the best you can hope for is that your original series will be less than the test series because you can show that it converges. So since the test series converging, you're hoping that the original series is less than the test series. But let's test it and see how it works out. So again, now back to this again. I've got an original series, and I want to compare this to the test series. Now, the original series converged, so the question is, do I want it to be less than or greater than? Since this one converged, I want it to be less than. Now, it may not turn out to be that way, but that's the way I'm hoping it's going to be. So I'm going to put a little less than here, and I'm hoping that this original series will be less than the test series. So again, the 4 doesn't make any difference on this. The constant doesn't, so I'll put it down like this. This will be the square root of n cubed plus 2, and I'm going to compare that to the square root of, and again, you can either write it as n to the 3/2 power, or in a way it might be easier to just rewrite it like this. So n cubed in the square root. So rather than writing it like this, I'm going to write it like this just because it looks more. Now what I want to know is this one less than this one. Now in this case, no matter what number I pick from n, when I cube it and take the square root of it, it's going to be always a little bit smaller than what I pick over here. So I pick that same number and add something to it and then take the square root of it, then this denominator here will always be just a little bit bigger than this denominator here. So if this denominator is bigger than this denominator, it means that this fraction is smaller than this fraction, and this would be, and again, it's like I've got a question mark here, this would be true. So if you need to, again, you can pick a couple of specific numbers. If you want to plug a 2 in and then a 2 for n here and a 2 for n here, you can kind of see. But also you can use the argument of which one has the bigger denominator. Well, that turns out to be true. So what this means is that you just showed that the original series, so the original series is less than the test series. And that's the second part. So now back to your definition. If you can show that the test series converges and the original series is less than the test series at every point, then you conclude that the original series must also converge. So if you come down here, the last step would be the test series converge, the original series is less than the test series, therefore the original series has to converge too. So this would be the original series converge. And let's work one more. So far, every one of them involved a p-series test. Let's take a quick look at one that involves a geometric series test. Now the idea is this one's a little bit different. It looks like this. So I will still do exactly what I've done before. I'll go ahead and bring the 3 to the outside. This will be the summation of n equals 1 to infinity. And this becomes 1 over 4 raised to the n power plus 2. Again, let's use the same thing. Dominant term, what happens as you go way off to the right? So you're trying to figure out what series would you compare this to? Well, if you go way off to the right, that plus 2 basically disappears, and this thing will turn into 1 over 4 to the n power. So going way off to the right. So this would be a good series to compare it to. But now, what have you got here? Well, let's kind of play around with this a little bit. This would be like having summation of 1 to the n over 4 to the n. Now, since both of them are to the n power, you can write that as the summation of 1/4 to the n power. And what this is, if you recognize it, it's in the form summation of a times r to the n power, or in other words, it is a geometric series. So this new series, the test series, is a geometric series. And remember to figure out whether this test series, and again, this is your test series right here, and this is the original series. So does a geometric series converge? Well, remember, if r is less than 1, then the geometric series converges. So this r is 1/4. In this case, r would be equal to 1/4, which is less than 1, which says that this series is going to converge. So in this step, you showed that the test, just like the other ones, you showed that the test series converges. And the only difference is, in those previous examples, the test series was a p-series. In this case, it is a geometric series. So you got the first part done. So now that it converges, again, it falls into this category right here. You showed that it converges. So your next hope is that the original series will be less than the test series at every point. So let's try that and see. So again, I've got the original series, and I'm hoping to show that it is less than, that's the only thing I can show that it converges on. I'll put a question mark. I'm not sure if it is or not yet, but I'm hoping to show that the original series is less than the test series at every point. So again, we go ahead and put this in. If I put 1, the original series would be 1 over 4 to the n plus 2. And I'm hoping to show, again with a question mark, that this is less than the test series, and the test series is 1 over 4 to the n. Now, using the same arguments we've always used, the denominator over here, this 4 to the n, will always be less than 4 to the n plus 2. So the denominator on the left is always going to be bigger than the denominator on the right. So in a fraction, if the denominator is bigger, the whole fraction is smaller. So this fraction on the left will always be smaller than this fraction on the right. So indeed, that inequality is true. And again, what that means is you showed that the original series, so it's going to be the original series, and you showed that it is less than the test series that you were comparing it to, less than the test series. So you've got that step done. And now you're really ready for the final step, which is just if the test series converges and the original series is less than the test series, then you can conclude that the original series converges. So you go back in your final step here, you can now finally conclude that this original series does converge. So the original series converges, and you'd be done. And one final look is that, in my opinion, if you kind of remember them this way, rather than remembering the more formal definition that looks like this, all this a sub n stuff, is if you just reduce it down to just these two right here, then I think it makes it a little bit easier what's going on. So again, if the test series converges and the original series is less than the test series, then the original series has to converge. If the test series diverges, the best you can do is show that the original series diverges. And if it doesn't specify these conditions, it's possible that the test may fail and you might have to try another test. But that's a quick look at the direct test for convergence.